Hello, welcome back to the channel. Today we're diving into something really exciting, a top-performing solution created by Zulo40 for the Lacuna Solar Survey Challenge on Zindi. This competition presents a fascinating problem, counting solar panels and boilers from aerial imagery combined with tabular metadata. This is exactly the kind of real-world challenge I love exploring, where multiple data types come together to solve an important sustainability problem. The solution we're examining today, created by Zulo40, achieved an impressive 0.98 MAE score on the leaderboard. What makes this solution particularly interesting is how it elegantly combines image processing with tabular metadata to improve predictions. Whether you're interested in computer vision, multimodal models, or just looking for techniques to boost your competition performance, this walkthrough has something valuable for you. Let's see how this model tackles the challenge of counting solar installations from drone and satellite imagery, and what clever architecture choices contribute to its success. Let's start by looking at the overall architecture of this neural network. As you can see from this visualization, we're dealing with a dual-input model. On one side, we have our image input that feeds into a powerful, efficient NetV2 B3 backbone. This pre-trained network extracts rich visual features from our drone and satellite images. On the other side, we have metadata inputs, specifically information about the image origin and the placement type. The image origin tells us whether we're looking at drone imagery, labeled as D, or satellite imagery, labeled as S. The placement types include categories like roof, open space, and others that describe where the solar panels are installed. What's really interesting is how these two paths come together. The metadata features are processed through a multi-head attention mechanism with 4 heads, which helps the model focus on the most relevant metadata aspects. Then, the attended metadata features are concatenated with the image features from our backbone. Finally, everything flows into a regressor that uses a softplus activation function, which is a brilliant choice for this type of counting problem, as it ensures non-negative outputs while handling the wide range of panel counts more effectively than a linear or logarithmic approach. Now, before we dive into the code itself, let's take a moment to understand the data distribution we're working with. These visualizations really reveal some important patterns that explain why certain model design choices were made. Looking at the heat map on the left, we can see the average number of panels based on placement type and image origin. What immediately stands out is how placement dramatically affects panel counts. Roof installations average only around 3 panels per image, while open space installations have much higher counts, over 15 panels for D origin images. The S unknown category, which represents satellite imagery, also shows high panel counts at nearly 15 panels per image on average. The box plot on the right shows us even more detail about the distribution. What's striking is how right-skewed the data is. Most installations have relatively small panel counts, but we have these extreme outliers, especially in the S unknown category, where we're seeing some installations with up to 700 panels. This extreme range from just a few panels to hundreds explains exactly why a softplus activation makes sense for the output layer. With linear regression, those huge installations would create massive gradients that would dominate the learning process and potentially destabilize training. The box plot also shows how the distributions differ by category. Roof installations are tightly clustered at the low end, while the open space categories show more variation and higher counts. The satellite-based images in S unknown show the most extreme outliers. This analysis really helps us understand why the model needs to handle such varying scales, and why the metadata about placement type and image origin adds so much value to the predictions. Let's dig into the code now and see how all this is implemented. First, let's look at the dataset class. This solar panel dataset class handles both the image loading and the metadata preparation. Notice how carefully the metadata is encoded. They're using a one-hot encoding approach for the placement types, which gives the model clear categorical information that's easy to process. The metadata is created as a 5-dimensional tensor, where the first dimension represents whether the image is from a drone or satellite, and the other 4 dimensions represent the different placement types using one-hot encoding. This structured approach to handling the metadata is really clever. Moving on to the model definition, here's where things get really interesting. The efficient NetVita Meta class implements that dual-path architecture we saw in the visualization. The backbone is an efficient NetV2B3 from the TIM library, which gives us a really powerful feature extractor pre-trained on massive image datasets. The metadata processing path is particularly well designed. First, we expand our 5-dimensional metadata into a 128-dimensional space, apply layer normalization for training stability, then array LU and dropout for regularization. After that, we reduce back to 64 dimensions before applying the multi-head attention. Speaking of attention, this is a really clever addition. By using a self-attention mechanism, the model can learn which aspects of the metadata are most important and how they interact with each other. When you're dealing with different placement types and image sources, not all metadata might be equally important for all predictions, so the attention mechanism allows the model to focus on what matters most. In the forward pass, we can see how it all comes together. The image features and attended metadata features are concatenated, and then fed through a final regressor network that outputs our predicted counts for both boilers and panels. The augmentation strategy is also quite comprehensive. For training images, they're using random resized crops, flips, rotations, blurring, contrast enhancement, and color adjustments. These augmentations make sense for aerial imagery, where orientation doesn't matter and lighting conditions can vary widely. Making the model robust to these variations is key to its performance. Moving to the training function, there are several sophisticated touches. They're using Huber loss instead of MSE, which is more robust to outliers, a smart choice given those extreme panel counts we saw in the distribution. Atom W with weight decay helps control overfitting, and the cosine annealing scheduler with warm restarts helps optimize learning rate throughout training. They're also leveraging mixed precision training with AutoCast and GradScaler, which speeds up training while maintaining accuracy. This is a great performance optimization that allows you to train larger models or with larger batch sizes. For model validation and selection, they're tracking MAE, mean absolute error, across epochs, and saving the best performing model for each fold. This makes sense since MAE is the evaluation metric for the competition. Finally, for inference, they're using an ensemble approach by averaging predictions across multiple folds, which typically improves robustness and performance. They train 3 different models on different data splits and then average their predictions for the final submission. So there you have it. A comprehensive breakdown of this impressive solution to the Lacuna Solar Survey challenge. What makes this approach stand out is how effectively it handles the multimodal nature of the problem, processing both image data and tabular metadata to achieve that impressive 0.98 MAE score. The solution demonstrates how combining computer vision techniques with structured data can significantly improve performance on real-world problems. From the efficient NetV2 backbone to the metadata attention mechanism to the carefully chosen softplus activation, every element works together to handle the unique challenges of aerial solar installation counting. I hope this walkthrough gave you some ideas for your own Zindi competitions or multimodal machine learning projects. These techniques can be adapted to many similar problems where you're working with both images and structured data. If you enjoyed this breakdown, please hit that like button and subscribe for more competition solution walkthroughs. I regularly cover interesting solutions from Zindi, Kaggle, and other platforms to help you improve your data science and machine learning skills. Drop a comment if you have questions about this solution, or if there are other competition winners you'd like me to analyze in future videos. Until next time, happy competing, and I'll see you on the leaderboards.